Okay, hello everyone. My name is Gautam Kaki. Today I'm going to talk about our work on bolt-on convergence in mergeable replicated data types, or MRDTs. If you don't know MRDTs, that's fine. I'm going to briefly introduce them in a bit. So this is a joint work with my students Prashant Prahladan and Nick Lushenko at CU Boulder. Okay, quick recap of replicated data types, or RDTs. So distributed applications often replicate their state across multiple geographically distributed replicas of the internet. Replication is done for a variety of reasons, including low latency, fault tolerance, and trust decentralization. And just as ordinary data types are a convenient abstraction to structure the state of a sequential application, replicated data types are a convenient abstraction to structure the replicated state of distributed applications. So what separates RDTs from sequential data types is that they allow multiple copies or replicas of the state to exist simultaneously and be updated independently without the need for immediate synchronization, right? Along with the guarantee that the replicas of the state will eventually converge to a single value, right? So intuitively, the converged state sort of preserves the effects of all the operations that are performed thus far at all the replicas. So that's briefly about RDTs. Broadly speaking, there are two fundamentally distinct approaches to replicated data types. Right? First is operation-based replication, where we apply commutative, non-conflicting operations at multiple sites. At multiple sites to replicate the state. So this results in what we all know as just sorry for the interruption. What we all know as conflict-free replicated data types, or CRDTs. The second approach is state-based replication, where we let concurrent versions of the state to evolve independently from a single common ancestor version, which are then merged into a single convergent version, right? So to be amenable for this approach, a data type has to define a three-way merge function to merge concurrent versions of the state in presence of their lowest or latest common ancestor, called LCA, into a single convergent version, right? And in fact, the presence of this three-way merge function is in fact what makes a data type a mergeable replicated data type. So MRDTs are inspired by distributed version control systems in general, and Git in particular. MRDT replicas correspond to Git branches, and synchronization between replicas is like analogous to Git pull and Git merge operations, right? So MRDTs and CRDTs are broadly two approaches to replicate data types. And as evident from the slide, they are both theoretically simple, but their theoretical simplicity belies the complexity of adopting them in practice to engineer convergent replicated data types. So what do I mean by that? Let's take a look at an example, right? So consider an execution of a set CRDT as shown on the slide. So we adopt a timeline view here where time sort of flows downwards, right? So we have an execution where we start with two replicas, R1 and R2, both of them starting with a singleton set E. R1 performs a remove, R2 performs a remove followed by an add. Then R2's remove and add are then applied in causal order at R1, right? Meanwhile, R1's remove also gets delivered at R2 and applied. Now observe that R1's remove and R2's add are applied in different order at these two different replicas, which results in a diverging state, right? A singleton set on R1 and an empty set on R2. So how do we fix this execution, right? So note that the network is already causally consistent. It already delivered messages in causal order. So clearly a causally consistent system is not enough to preempt this anomaly. The contention here is about the relative ordering of concurrent adds and removes, which are on the same element and therefore conflict, right? So what we need is a stable arbitration semantics, something like add_fins, which consistently orders concurrent conflicting adds after removes, right? But implementing this arbitration order is not easy, as we now have to track element-wise causal dependencies, perhaps using the vector clock for each element. And this is not going to be easy, right? Because it requires a significant reengineering of the usual set data structure. Okay, so that's the story of set CRDT. But what about a set MRDT? Does adopting a state and version-centric model of replication sort of alleviate this problem? Let us see, right? But before we discuss the set MRDT, we have to understand the semantics of set merge, because for a data type to be MRDT, it has to necessarily define a three-way merge function to reconcile conflicting versions in presence of their LCA version, right? Now, how do we define such a merge for a set, such a merge function for set? Well, a straightforward set merge function would remove any elements that are removed on the either side and add elements that are added on the other side, right? So simply stated, the merged function must contain elements that are common on between all the three versions, the ancestor version and the two concurrent versions. So these are the elements that are left untouched, along with any newly added elements on the left side and newly added elements on the right side. So that's it. So that constitutes our set merge function. Now, equipped with this set merge function, we can now consider the executions of set MRDT, right? So like the CRDT, the MRDT starts its execution with a singleton set containing a singleton set containing element E. We have two replicas which correspond to two branches. So we can think of these two branches sort of forking off from this initial version, right? Both initially perform a remove to remove the element E, resulting in versions V1 and V3, right? Now, to propagate R2's changes onto R1, we merge R2's version V1 onto R1's version V3 to produce version V4, right? The latest common ancestor LCA of V1 and V3 is the initial version V0, which is a singleton set. And if you look at how V3 and V1 came about from V0, we see that starting from V0, V3 removed an element and V1 removed an element, the only element, and therefore the merged version V4 is simply an empty set, right? Okay, next R2 re-adds E to generate version V2, following which R1 again merges latest version V2 with its latest version V4 to generate V5, right? The LCA for this merge is clearly V1, which is an empty set. Starting with V1, nothing is added on the left-hand side, whereas E is added on the right-hand side, and therefore the merge result is a singleton set E, right? Now, concurrent with these merges, another merge happens at R2, pulling the changes from R1. So this merge sort of merges version V3 with version V2 to produce version V6. The LCA for this merge is the initial version V0. On the left-hand side, E is deleted. On the right-hand side, nothing happens. Therefore, the merge is essentially an empty set, right? The result of merge is an empty set. Okay, so this is this finishes the MRDT execution analogous to the CRDT execution. Now, unfortunately, what we see is we end up with different versions on replica R1 and R2, right? R1 has singleton set and R2 just an empty set, which is bad, right? So what's the key takeaway from this story? Well, the key takeaway is that moving to a state and merge-centric model of replication is not going to magically fix our problems. We need something more to guarantee the convergence of MRDT executions, and that something more is in fact the focus of this work, right? In particular, right, what we propose is a distributed runtime for MRDTs called Quark, right? Which is supposed to be bolted onto MRDTs, right? So Quark is unique in the sense that it orchestrates well-formed MRDT executions, which are guaranteed to converge regardless of specific merge semantics of the data type, right? This means that you can simply bolt on Quark to any MRDT and obtain convergence without having to prove additional properties or merge functions. And this is a big deal, right? A notable aspect of Quark is that it does not interfere with replica local evaluation, so it has no effect on per operation latency and replica availability, right? So consequently, one can safely bolt on Quark without losing key performance characteristics of replicated data types. And how is this possible? Well, the key observation that makes all of this possible is that merge is a total function, which means it can be used to merge concurrent states that are arbitrarily far along, provided that those concurrent states have a unique lowest common ancestor. Well, remember this condition because this is the devil that is lurking in the detail. But assuming that concurrent states have always have a unique lowest common ancestor, we can always merge concurrent states, and therefore we can arbitrarily delay merges, right? Since we can arbitrarily delay merges, we now have the freedom to synchronize and orchestrate them in a way that guarantees convergence. And that's the key observation, right? So that's the enabling observation behind Quark. But then what's the downside of this approach? Well, the downside is that delaying merges arbitrarily result in replicas trailing behind each other for an arbitrary periods of time. And therefore, the entire system takes longer to converge, right? So we characterize this phenomenon using a metric we call staleness. So staleness is basically a metric that we consider, well, staleness has been defined previously, but it's something that in the context of RTTs, we consider it for the first time here, right? So our work basically effectively adds a new dimension to the discussion on RTTs by considering staleness as a novel trade-off. In practice, this means that application developers can obtain bespoke replicated data types suitable to their needs with little effort, but at the expense of some staleness. How much staleness? Well, we're going to characterize it with experimentally in in a bit of time. But the upside is that the staleness is quite tolerable in practice. Okay, so what are the key intuitions behind Quark? Well, the key intuitions, we will demonstrate key intuitions with help of an example, right? So let's reconsider the MRDT execution that we have seen before, which we know to be diverging, right? So one notable aspect of this execution is that mergers into R1 and R2 are concurrent. They clearly cross each other, right? So we call these crisscross mergers. Such mergers result in different interpretations of executions along different branches, right? For example, on the left branch, R1 interprets the execution as a remove followed by an add, whereas on the right branch, R2 executes its execution as remove followed by an add followed by a remove. So we have two sort of irreconcilable views of the same execution, right? So how do we sort of fix this? We observe that we can avoid this situation by effectively linearizing merges. That is, by executing them one after the other, such that each merge pulls the latest version from each branch, from the origin branch, instead of a previous version, right? So instead of merges being concurrent, if you can linearize the merges, we can sort of avoid the situation. So that's the first observation, right? So in this particular example, we can linearize merges in three different ways, either by ordering R1's merge before R2's merges, or between R2's merges, or after R2's merges, right? So these lead to three different executions with linearized merges. However, all the executions have the same sort of quote unquote advent semantics, resulting in convergent final state containing a singleton set E, right? So the key takeaway from this exercise is that by linearizing merges, it is possible to ensure convergence without constraining how and when individual operations such as add and remove are executed, right? That's a key observation. So in this example, it's sort of quite clear what we mean by linearizing merges, right? But is it always so trivial? Well, it turns out not. Semantics of linearizing merges is not always as obvious as for this example. So let's understand that with help of another example. So we consider an execution now containing 4 replicas, R1 to R4, each starting with a singleton set, right? Initially, R2 and R3 perform a set of operations on the set resulting in versions V1, V2, and V3. Then these versions are then merged into R1 and R4, one after the other, resulting in versions V4 to V6 and V7, V8, right? So the final versions, even after merging all the changes from R2 and R3, the final versions on R1 and R4 diverge, right? They have the version on R1 is a singleton set, whereas on R4 it's as an empty set, right? So this is a problem. Now observe that here there are no crisscross merges, right? Each merge sort of pulls the latest version from the branch at that particular point of time. Okay, so just to show that this is indeed the case, I'm going to quickly run through this execution to demonstrate that merges are indeed linearly ordered, right? So we have our initial version on V1, then on R3, then R1 sort of merges V1 to V4, then it merges the latest version on R3 to create V5, then R3 creates a new version V3, then R1 again merges the latest version to produce V6. R4 then wakes up and merges the latest version on R3 to produce V7. And then it merges latest version on V1, on R2 to produce V8, right? So basically we have all the merges are sort of linearized in time, right? And yet the final sort of result diverges. So we don't have a single unified view of the computation. So this is unfortunate, right? Because we have linearized merges and still we haven't gotten any better. We haven't done any better. But however, there's a way out of this problem, right? A key observation we make is that the lack of this unified view of computation sort of manifests structurally in the execution graph. What do I mean by that? Now observe that in this execution, versions V6 and V8 have two latest common ancestors, LCAs, right? So V6 and V8 have V1 and V3 both as lowest common or least common ancestors, right? Both are common ancestors for V8 and V6, and both are latest or least because there do not exist any versions that are later than these versions that are still common ancestors of V6 and V8, right? So we have a situation where we have two versions on different branches with two different LCAs. And this is a problem because presence of two LCAs enforces alternative explanations of how versions V6 and V8 came out to be. So along blue arrows, we see that R1 and R4 started with an empty set. R1 adds any, whereas R4 does nothing, right? And along red arrows, we see that R1 and R4 forked off a singleton set E. R1 does nothing, and R4 basically sort of removes the single element E, right? So we basically have two views of computation depending on what LCA we are looking at, right? And these alternative views of computation are irreconcilable, leading to divergence. We see the same pattern in the earlier MRDT execution as well, right, which was also diverging. Here, versions V5 and V6 have two different lowest common ancestors, enforcing two irreconcilable views of computation. Right. So from these examples, we observe that execution graphs with multiple LCAs are ill-formed, right? In fact, we discover that multiple LCAs is a necessary condition for divergence. Now, which means that absence of multiple LCAs or uniqueness of LCAs is a sufficient condition for convergence. Now, that is a big deal because we can now enforce convergence in all MRDT executions simply by enforcing the unique LCA property. And unique LCA property is a structural property and not a semantic property. So enforcing it is not actually quite difficult, right? So in fact, we can easily enforce the unique LCA property at runtime with help of a bit of synchronization in the background, right? And that is precisely what Quark does, right? So that's the intuition behind Quark, right? So, and this is a slide just to show that we have done all the math. All of this is formalized, and we have proven the soundness of this strategy of linearizing merges and enforcing unique LCS. We have proven the convergence and progress properties, which ensure that the entire system converges and can always make progress, right? The distinguishing or the notable aspect of our operational semantics is that our abstract machine, which manifests Git style executions, does not make any assumptions about the merge function, right? So the only thing that we require of the merge function is that it better be a function. It better be a complete function, right? Other than that, no other constraints are imposed. And yet we could, with help of this formalization, we could guarantee the convergence and progress properties, right? Okay, we've also implemented Quark runtime in OCaml. And here we show key characteristics of the implementation. One notable aspect is that we actually offload low-level concerns such as replication and fault tolerance to an off-the-shelf data store. In our case, it's Shyla, which is a C++ implementation of Cassandra. On the top of that store, we actually implement Quark as a runtime, right? So what Quark essentially does is basically it maintains a version history, it does background merges, and using version history, it sort of enforces this unique LCA property by making appropriate checks, right? And one more important optimization we implement is content addressability, which is that all the data structures are laid out on a content addressable store, which sort of maximizes the sharing between various versions of data structure, right? So propagating versions on the network sort of now becomes involves less overhead because we can just only propagate this, right? We have written multiple applications with MRDTs written in this style. For instance, we have TPCC application, which is a warehouse application written with help of red-black map RDTs, which runs on top of Quark, which in turn runs on top of our distributed store, right? We have evaluated our implementation on a few benchmarks, but we'll talk about collaborative editing application here. So the collaborative editing application basically replicates a buffer of characters across multiple nodes. So our document is essentially a list of characters, right? So each user connects to a node and forks of their own branch, and they make edits in their own branch, right? So basically each forked branch is a user's private replica, right? And there are as many replicas as there are users. So for our experiments, we have deployed all of this in Amazon West Data Center. Okay, so users make edits at an average human typing speed, which is 240 characters per minute or 4 characters per second, which works out to be around inter-edit latency of around 0.25 seconds or 250 milliseconds. So a version is committed after every edit, right? Merges happen in the background. Quark is responsible for merging things in the background. And with steadily increasing number of replicas, by number of replicas, we mean the number of concurrent users, number of concurrent editors. We measure the latency of each edit which is the time it takes to make an edit and save a version to the disk. And we also measured the staleness of each merge, which is the time it takes for a remote version to be merged onto a local version, right? So here are our latency results. So it's latency pretty much remains constant. The median and 10th percentile latencies remain around 10 milliseconds. The 98th percentile latency show an initial bump and later sort of even out. We find that this bump is due to our idiosyncrasy of our implementation, which uses OCaml lightweight threading. We hope that when we move to multi-core OCaml, this sort of pattern sort of evens out, right? Okay, just to put things in perspective, we've also measured the latency of a SE edit, which is another way to guarantee convergence without proving associativity, commutativity, etc. So with SE edits, the latency sort of quickly grows and it reaches nearly 2 seconds. So compared to SE edits, so the Quark edits are sort of pretty much remain constant. The latency remains constant and much lower than the latency of an SE edit, right? But more interesting measurements are staleness measurements, where we measure basically the time it takes for a version to propagate across the network and get merged into another version, right? So it's not just the network latency and of course the disk latency, but also the time it takes for Quark to allow this merge, to determine this merge to be legal and allow this merge, right? Okay, so we know that the staleness essentially increases with the increasing number of concurrent editors. This is log scale, so the increase is sort of linear, pretty much linear. For 10 concurrent editors, the staleness is around 100 milliseconds. For 60 concurrent editors, the staleness jumps to around 2 seconds, right? So yeah, so staleness, although for fewer editors, the staleness is manageable, it quickly jumps as we increase the number of concurrent editors, right? But however, I'd like to note that the staleness per 10 concurrent editors, which is 100 milliseconds, is much lower than the inter-edit latency of 250 milliseconds. So the staleness we assume is not really noticeable, right? And also the staleness measurements include disk I/O latency, and future when we implement an in-memory data store, sort of we assume, this disk I/O latency might go away, right? Okay, so that concludes our discussion on Quark. So what's the upshot? Well, the upshot is that it's now possible to build convergent replicated data types without re-engineering sequential data type implementations and without proving algebraic properties such as commutativity and associativity, right? So this we hope would bring RDTs sort of accessible, closer to regular application developers, right? Runtimes help, like Quark demonstrates. And there's a new dimension to the discussion of trade-offs in the realm of RDTs, which has not been considered before, which is the staleness versus ease of implementation trade-off. So Quark essentially is the system that sort of explores this trade-off and characterizes staleness, etc. Right? So that's all I want to present today. Thank you all for listening. So a dirty version of Quark implementation is available at the URL shown there. We'll in the near future release an open source version of Quark. Thank you.